This is the second section of chapter 8, which is all about numerical methods, and this is solving second order differential equations. Now this is going to be extending Euler's method. So previously what we've done is we've derived an iterative formula to solve a first order differential equation, and that's based on the fact that the dy dx is approximately equal to the change in y, also write the change in y, over the change in x. And the change in y, well, we called that y1 minus y0, and the change in x, well, that was just h. Now we can extend this and say, right, okay, if it's the second derivative, how do we define the second derivative? Well, the second derivative can be defined as approximately equal to the change in dy dx, so that's the change in the first derivative over the change in x. So the change in y dx, we could write that as dy dx at a certain value. Let's call that 1 minus dy dx at a different value, an initial condition, 0, divided by the change in x, and that's still going to be h. Okay, I've added a diagram because this is now going to help us to fill this in with values of x and y. So we're going to start by working out the gradient at this point here. Now the gradient at that point, which will be dy dx at this minus 1 here on x minus 1, well, that's going to be approximately the change in y over the change in x. Remember, the change in x is h, so this is approximately y0 minus y minus 1 over h. Okay, so that represents the approximate gradient here. Now we're going to do the same thing at this point here, and we'll write down what the gradient is approximately for this line section here at this point. So now this is the gradient where our initial conditions are, and this will be approximately, again, a change in y, which will be y1 minus y0 over h. So now what we've got is these gradients, which we can now plug into here. Now I know I've got 0 and 1, but I can swap this for, 1 and 0. I can put 0 here and negative 1 here. So I could actually say, right, that this is actually the same as dy dx 0 minus dy dx minus 1 over h. Yeah, so that allows me to use what I've got here. So we'll put that in and we'll say, right, the second derivative is going to be approximately, so dy dx 0 will be y1 minus y0 over h minus y negative dy dx minus 1, which is going to be y0 minus y negative 1 over h, all over h. So all I've done is just substitute these, or these ones here, for what I've written about the gradients. And if I simplify this all out, what I will get is d squared y over dx squared is going to be approximately, so I'm dividing by h here, dividing by h again. So I'll end up with h squared at the bottom because I'm like dividing by h and dividing by h again. And these bits here will simplify. I will have like a y1, then negative 2 lots of y0, and then plus a y minus 1. So we'll put that down all over h squared. So that will become y1 minus 2y0 plus y negative 1 all over h squared. So we're just going to rearrange this into a form that's going to be usable, because we want to find y1. Remember, the whole point of using this numerical method is that so we can estimate values of y. So y1 is going to be approximately 2y0. So I'm just rearranging what I did before. Minus y minus 1 plus h squared times by d squared y over dx squared 0. So I suppose I should add here that actually this is what I was doing, working out the second derivative, or an estimate for the second derivative at 0. And we can now turn this into a iterative formula by using r. So we'll have y r plus 1 is approximately 2yr minus yr to the minus 1. So we're basically just looking at these numbers here. So if this is r plus 1, that will be r. This will be r minus 1. And then plus h squared times by d squared y over dx squared r, and this is for r equals 1, 2, and so on. So this is, starting from 0, 0, 1, 2, so on. So this is the bit that we're interested in. So I'll just highlight this here. Now, often what you'll see in these questions is it will give you the approximation that you're going to use, and it's basically going to be this. You can rearrange the approximation that they give you into this form. Okay, so let's look at what we've been given in this question. So first of all, we've been given this second order differential equation. We've been given t equals 0, x equals negative 1, and this dx dt is 3. So these are all our initial conditions here. Yeah, so I'll just write down initial conditions. I'll write those down in a moment. We've been given what approximations to use, okay, to find dx dt and d squared x over dt squared. And we want to find estimates for x for t equals 0 and t equals 0.2, and we want to give our answer to 4 decimal places. So the first thing that strikes me about this question is, most of the other questions we've done have been dy dx, but this one is dx dt, so we need to be careful. So in the iterative formulas that we've been using, just make sure that where we see a y, we've actually got an x in this question, and where we'd normally see an x, we've got a t in this question. Right, and I can see from here as well that the step size h, let's write this down, is going to be 0.1. Right, so just like before, we're going to use the table. So the first table row is going to be r, then we're going to have tr, so t0, t1, t2, t3, then xr, then dx dt, r, and the second derivative r. Now we may not need all of these boxes, but it just helps us with our working. Now initially t0 is 0, so we'll fill in that first row, and xr is -1, or x0 is -1, and x dt0 is 3. So there are our initial conditions. Now our step size is 0.1, so we're going to need a second row where we do 1.1, oh sorry, 0.1. We'll put that in, and then our last row is going to be when r is 2, so 0.2. So this question is really about working out what number goes here and what number goes here, and we'll just blank off the rest of this table, we won't need it. Okay, so basically filling in all the initial information that's been given. Now we want to start to fill this in, and actually I can find x1 straight away by using this approximation here, because I know x0, that's -1, I know h, that's 0.1, and I know dx dt 0, the gradient initially, which is 3. So if I use that, so using dx dt 0 is approximately x1 minus x0 over h, I can find x1. So let's fill in the numbers. So what do I have? 3 here for dx dt. X1 is what I want to find. X0 I know is -1, so minus -1, all over h, which is 0.1. So from there it's just quick rearranging. So x1 will be approximately 3 times 0.1 minus 1, and you'll recognize that basically as Euler's method. Yeah, so these approximations here, we rearrange them, and it's basically Euler's method. Right, so that will give me x1 is approximately, so at -0.7. So let's fill that in the box, -0.7, and what we've got is our first answer. Let's put that in, -0.7. Answer number 1. We now need to work out what goes in the box below. Now I want to find x2. This is where I use the second formula. Now you notice there's no x2 in there, but remember we use this like an iterative formula. So if this is 1 here, this becomes x2, this becomes x1, this becomes x0, and h doesn't change. So by using that, let's just underline this here, I can say that dx squared dt squared 1 is approximately x2 minus 2x1 plus x0 all over h squared. Now let's think about this. What have we got so far? Well, I have x1, I've just worked that out, I've got an approximation for that. I have x0, that's -1, got that. I've got h squared. Okay, this is what I need to find. Now the only other known that I haven't got is this, but I can use the second order differential equation that I've been given up here to work out what this is, because to work this out, what do I need? I need x1 and t1. So let's work that out over here. So d squared x over dt squared 1 is equal to, so all I'm doing is now rearranging this. So I can take all of this, put it on the other side. So it will equal sine x plus t, or in my case, sine x1 plus t1. Right, so that will be d squared x dt squared 1 will be the sine of x1 and t1, which we have here in our table. So that will be negative 0.7 plus 0.1. And we'll work that out on my calculator. Remember, we're in radians. So I get negative 0.56464 and so on like that. And I'll make sure that when I do my working, I use the exact answer here. Now remember that goes here. So now we have this value as well. So our equation now becomes negative 0.5646 ... is approximately x2 minus 2x1, 2 times x1, x1 is negative 0.7, plus x0, well that's negative 1, that's our initial condition, all divided by h squared, which is going to be 0.1 squared. Once we've done this, we've got our answer. So we can rearrange this and say that x2 is going to be approximately 0.1 squared times by, and here I will use my answer button. Yeah, and then I will have plus 1.4 from multiplying that out, so I'll do minus 1.4. And then this will give me negative 1, so when I move it across it will become plus 1. And maybe you'll recognize this from what we derived before, because here we have x2 is approximately 2 times x1 minus x0, so minus negative 1, plus h squared times by d squared x dt squared at 1. Yeah, so this is basically what we derived before. So from this, what we'll get approximately for x2, using my calculator and the answer button, so I get minus 0.40564, and it carries on. So that will basically be what goes in this box here, minus 0.46, like that. So let's write down our solutions. So my approximation for x1, that's approximately negative 0.7. My approximation for x2, if I'm giving my answers to 4 decimal places, so I should really write this for the first one, and for the second one, negative 0.4056. So there we go. Okay, so here it says the curve y equals f of x satisfies this differential equation, which is here. Now notice this differential equation is different to the previous one in that it includes dy dx. The last one didn't have that, so we need to consider that when we do our working. We have our initial conditions here. The initial conditions. What else do we have? We've got the approximations that they want us to use, so we'll use those. Again, it's just Euler's method. Saves us having to remember what it is. It's easy enough just to substitute into there. With h equals 0.2, so we've got the step size. and we want to estimate the value of y when x equals 1.2. Okay, so it looks like we're only going to have one iteration. So let's start with our table R, and it's x and y this time. So x r, y r, dy dx r, and the second derivative r, d squared x over dx squared r. Right, we start with r as being 0, and then 1, and so on. So let's see how much of this table we need. So we have the initial conditions, let's put those in. So we have x0 is 1, y0 is 4, dy dx0 is 3. So those can go in. We know that the step size is 1.2, so basically our table is just going to have 2 rows. In this question, it is all about working out what number is this. What number goes in this box here? Now, the first thing you might notice is this is slightly different to the last example because of this bit here. In the last one, I think it said something like x1 minus x0. We knew that. We don't know y minus 1, so I'm just going to highlight that. So we can't find, or we can't use this equation here on its own because, well, y1 is going to be unknown. That's what we want to find. That's what goes in this box. But also y negative 1 or y minus 1 is also unknown. So we're going to have to use it along with this equation here. Now this has y minus 1 in it, and we can use them simultaneously to eliminate this. This is what we want to find. So this is known, this is known, this is what we want to find. We can eliminate this if we use this equation here. But to use this equation, we need this, don't we? We need to find out what is this value, and we can work that out using this. What is the second derivative using the initial value? So we're going to find this first. Once we've found that, we can write an equation that has this as unknown. We'll solve it simultaneously with this equation with this unknown, and then we can find y1. So slightly different to the last one. So let's work out dy squared dx squared initially. So that will be using x0, y0, both squared, plus what dy dx is initially. So what will that give us? So we've got all of those initial values. So that's going to be 1 squared plus 4 squared plus 3. So if my maths is right, 1 plus 16, 17 plus 3 is 20. So we'll put that in the table. So this value here is 20. Right, we can now use that and we'll put it into this equation here. So what can we say? That 20 is approximately y1, which is what we're trying to find, minus 2y0, well, y0 is 4, plus y minus 1, well, we don't know that, but we're going to eliminate it in a moment, all divided by h squared, and h is 0.2, so it's 0.2 squared. So what we might want to do is just rearrange this to make maybe y1 my negative 1 the subject, or y1 the subject. So I think what I'll do is I'll rearrange it to make y1 the subject. So y1 is going to be approximately, now so we've got 20 times by 0.2 squared Then we've got minus 8, so we'll plus 8, and then it'll be minus y negative 1. So that can be tidied up a bit to give me y1 is approximately, so 20 times by 0.2 squared, which is 0.8 plus 8, which is 8.8 minus y negative 1. Right, so that's my first equation. So I will now use this one here and do something similar. And because my y negative 1 is unknown, I can just substitute it into the other equation. Right, so we have dy dx 0 is approximately y1 minus y negative 1 over 2h. So dy dx 0 we have is 3. y1 we don't know, that's what we're trying to find. Y negative 1, again we don't know, but we can eliminate it, over 2h, so that's 2 times by the step size. So that can be rearranged to make, well, it doesn't really matter really. We'll make y negative 1 the subject so I can substitute it in. Right, so I would have 3 times by 0.4 is approximately y1 minus y negative 1. And rearranging that to make y negative 1 the subject so I can just substitute it in, I will have y1 minus 1.2. So this will get substituted into, that's a bad line, let's try again. We'll substitute that into here. So we'll have y1 is approximately 8.8 minus y negative 1. Now y negative 1 we've just worked out is y1 minus 1.2. So y1 is approximately 8.8 minus y1 plus 1.2. So we can add y1 to both sides, so we'll have 2y1 is approximately 8.8 plus 1.2, which is 10. So we'll get y1 is approximately 5. So there we go. That will be our final approximation for the value of y1. So you should now be able to do exercise 8b on pages 171 to 172. As usual, a quick recap of what we've done. So basically we extended Euler's method to the second order differential equations, and we started by saying, right, if you want to find the second derivative at the initial conditions, we can work it out like this. So this is basically what we get when we work out the change in dy dx over h. That can be rearranged into an iterative form. So yr plus 1 is approximately 2yr minus yr minus 1 plus h squared times by d squared y over dx squared r for r equals 1, 2, and so on. When you do these questions, I would suggest that you use a table. Yeah, and then in your table straight away you can fill in the initial conditions that are given. once you've got those initial conditions put in, then you can use your second order differential equation, okay, to find, for example, what the second derivative is initially. You'll notice in the second example we couldn't do that directly, so if your approximation that you're given, or if your approximations both involve y minus 1, then you may need to solve simultaneously, so just be aware of that. And actually, let's change that. It won't be y minus 1, it would probably be something like x minus 1. Well, it could be, or y minus 1. All depends on the question.